Hello everyone, I am Abhijit Budathoki and welcome to my YouTube channel. On this video, that is part 3 on the date and calendar method, we are going to discuss the theory behind this date and calendar method that I discussed in first part of this video, and that I showed some applications of that trick in second video. So for this, let's start with first day of AD. That would have been 0001, that's January, and the first day 01. And it's not sure that if there ever was this date, right? Because there used to be different calendars in the past. Julian and later Gregorian calendar was added. So the trick we are performing is applicable on Gregorian calendar. So Gregorian calendar was added much later in the history. So we suppose that according to the Gregorian calendar, this date was Monday. This date was Monday. Now this trick is very much based upon finding the odd number of days in month, in year, in leap year, in century leap year, in century, right? So first of all, let me describe what the odd number is. So suppose we have 1, 2, 3, 4, 5, 6, 7 as the days of this first January of first AD. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, right? So since we know that the first day of the first AD of the January is Monday, so this is our Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, again Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and there is 21 Sunday, 22 Monday, right? Now let's discuss here. If I divide 7, this 7 by 7, and keep the remaining part, that is modular division, 7 mod 7. Let's just remember that mode gives us the remainder. So if 7 mod 7 gives us, we know 0, because 7 is exactly divisible by 7, and for 0, that means we have 0 number of odd days, and 0 number of odd days means that the day must be previous day than the Monday, right? That must be what? Sunday. We can see here that the 7th date is Sunday, and this 0 number of odd days means Sunday. Similarly, let's divide 8 by modular divide 8 by 7. This will give us 1, right? And again we have, what is this? This 1 corresponds to Monday. So 9 mod 7, the number of odd days are the remainder part of this, that is 2, 10 mod 7, 3, again we come to 0, right? In this fashion we can keep on going and going, but this the days keeps on repeating, because if we have 0, here we can see 7th date is Sunday. Similarly, if we have 1, the date is Monday, 2 Tuesday, right? 9 is Tuesday, and 10 is Wednesday, Thursday, Friday, Saturday. Now this is Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. The similar goes on here. 14 is what? Sunday, as you can see. 15 is Monday, 16 is Tuesday, 17 is Wednesday, 18 is Thursday, and 19 is Friday, 20 is Saturday, and the 21 again is Sunday, and the 22, if we divide 22 mod 7, then this will give us the remainder 1, and 1 again corresponds to the Monday. So from this we can conclude that we have codes, as the number of odd days. Codes is the number of odd days for different day of the week. So the first code that we have here is, if the number of odd days comes to be 0, then it's a Sunday. 1 Monday, 2 Tuesday, 3 Wednesday, 4 Sunday, Thursday, 5 Friday, and 6 Saturday. We also notice that the number of odd days could be from 0 to 6, right? Because if it's 7, then 7 is modular divided by 7, and the remainder comes to be 0. So this keeps on repeating, and we have the code for the day of the week. Day of the week. We will use these codes for finding the day of the week. Now let's move on to the month part of this. Okay. In general, what we have is, we have two types of years. Two types of years. One is general year, and another is leap year. We know that leap year comes after every 4 years, and leap year is that year which is exactly divisible by 4. We can check if a year is a leap year or not by dividing it by 4 and observing if it's exactly divisible by 4 or not. And if it's not exactly divisible by 4, then it's a general year. So in general year, now we will list the month and their corresponding days here. We have 1st January, February, March, April, May, June, July, August, September, October, November, December, right? Now in general year we have 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31, right? Then in leap year we have 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31. Now let's find out the number of odd days for each month, right? We have 3 possible values, right? We have 28, 30, 31. Sorry, in the leap year the number of days in February is 29. We must not forget that, right? So we have 4 possible values for the number of days in a year. 28, that is unique to February in the general year, and 29 is unique to February in the leap year, and 30 for we can see April, June, September, November, and 31 for all the other remaining months, right? Now let's perform modular 7 in each. Modular 7, this will give us 0. Mod 7, this will give us 1, because 7 times 4 is 28, and the remainder is 1. mod 7, this will give us 2, mod 7, this will give us 3. So we have corresponding number of odd days is 20, for 28 0, for 29 1, for 32, and for 31 3. Now we can write for 31 3 3 3 3 3 3 3, and then for for finding out for 30, for the month with the 30, the code is, or the number of odd days is 2 2 2 2, and for 28 the number of odd days is 0, right? Similarly here in leap year, all the other number of odd days are same except for February. Number of odd days for 31 3 3 3 3 3 3, for 30 2 2 2 2, and for 29 we have 1. Here it is number of odd days, right? Number of odd days. Now if we suppose we are finding the day of May, then up to May the April must have passed, right? April is already gone, so the code that we should be using in May belongs to April, right? So what we need to do is we need to transfer, or we need to transfer each number of odd days, or translate this number of odd days one step down, right? Because the code that's in January 3 will be used in February, because the number of odd days, while finding the day of the February, we must be using the number of odd days January. So let's move each number of odd days one step down. This will give us 3 0 3 2 3 2 3 3 2 3 2 3, and here we will have one step down, right? This will give us 3 1 3 2 3 2 3 3 2 3 2 3. Now let's find out, while calculating the June, we do not want to calculate the number of odd days in each month, right? So we need to find what is cumulative number of odd days. So if we have to find out the day of the February, then we need the number of odd days up to January, right? We have already moved one step down, so this is our up to this. We need to find out the code up to this. For finding the day of the July, we need to find out the number of days up to June. So we have already stepped one down, so we need to find out up to here, right? So for that, let's figure out the first number of odd days here. For January is, we can see 0, right? And if we add 0 3, this gives us 3 3 0 3 3 3 6 6 2 8 8 3 11 11 2 13 13 3 16 16 3 19 19 2 21 21 3 24 24 2 26 26 3 29. Now what we need to do is perform modular 7, because there are some numbers which are greater than 7. So 0 mod 7 gives us 0, 3 mod 7 gives us 3, 3 mod 7 gives us 3, 6 mod 7 gives us 6, 8 mod 7 gives us 1, right? And then 11 mod 7 gives us 4, 13 mod 7 gives us 6, 16 mod 7 gives us 2, 19 mod 7 gives us 7 to 14, 5 19, and this gives us 7 3 21, so 0, 7 3 21 plus 3 24, 7 3 21 plus 5 26, and 7 times 4 is 28, plus 1 is 29. We will find that this one that does not relate to any month will relate to the whole year, right? Because we are constantly adding the number of odd days up to that time, right? Up to December, the number of odd days are, when the December passed, when the December is finished, the number of odd days up to that is 1. And we will also relate this when we match the number of odd days in a general year with this 1 here, and here we will have number 2. Let's check if we come to 2 or not, right? So now the cumulative number of odd days here is 0, 3 plus 3 0, and then 0 plus 3 0, 0 plus 3 3, 3 plus 1 4, 4 plus 3 7, 7 plus 2 9, 9 plus 3 12, 12 plus 2 is 14, 14 plus 3 is 17, is 20, plus 2 22, plus 3 25, plus 2 27, plus 3 30. Now we need to again perform modular 7. Modular 7. If we perform modular 7, then 0 mod 7 gives us 0, 3 mod 7 gives us 3, 4 mod 7 gives us 4, 7 mod 7 gives us 0, 9 mod 7 gives us 2, 12 mod 7 gives us 5, 14 mod 7 gives us again 0, 17 mod 7 gives us 7 to 14, and we have 3, 14 3 17, 7 times 2 is 14, 14 plus 6 is 20, 7 to 14, 7 3 are 21, right? 21 plus 1 is 22, so 22 mod 7 gives us 1, 25 mod 7 gives us 4, 27 mod 7 gives us 6, and finally 30 mod 7 gives us 7 times 4 is 28, and 28 plus 2 is 30. Now we can check that for leap year the number of odd days when the December just finishes is 2, and the number of odd days for the general year is 1. Now here interesting thing arrives, right? If we divide the we have 12 cores, so that is very hard to remember, so we divide it in the groups of 3. First group is 0 3 4, second is 0 2 5, third is 0 3 6, and the last one is 1 4 6. This is for the whole year, right? This is for whole year. This one here is also for whole year. Now an interesting thing happens here. If we add 1 in each of the cumulative frequency here, we will find an interesting result. Let's look that for ourselves. Okay, 0 plus 1 gives us 1, 3 plus 1 is 4, 3 plus 1 4, 6 plus 1 7. But if I perform 7 mod 7, then I am again having the number 0, and then 1 plus 1 is 2, 4 plus 2 is 4 plus 1 is 5. We are adding 1 in each of these numbers, so 6 plus 1 is 7 again 7 mod 7 gives us 0, right? 2 plus 1 is 3, 5 plus 1 is 6, 0 plus 1 is 1, 3 plus 1 is 4, and 5 plus 1 is 6. Now let's compare these numbers with this set of numbers. What we see is the first 3 numbers are different, right? Here is 1 4 4, but here is 0 3 4. But after that, here is 0 2 5, here is 0 2 5, here is 0 3 6, and here is 0 3 6, and the last one is 1 4 6, 1 4 6, right? So if we add 1 in the number of odd days that we find here, then this gives us an interestingly similar numbers. So since we have added 1 here by ourselves, we have to subtract -1 while doing the calculation, right? For what year? General year. And for calculating, we haven't added anything here, so we have to subtract what? 0. So this is our correction factor, right? For making these numbers memorizable, we have added here 1, so we must subtract -1, but we have done nothing here, so we are going to subtract nothing. That means we are subtracting 0, which is nothing. So for the type of year, this correction factor will be taken in our calculation is type of year code, right? Type of year code, type of year code, that is -1 for general year. For general year the code is -1, and for leap year the code is 0. For leap year the code is 0. Then comes the code for month, right? Month. We have already calculated the codes for month here and here. We can see that there are codes, specific codes for general year and leap year. For general year we have 144 025 036 146, right? 144 025 036 146. And for leap year we have 034 034 025 036 146, which is, we can see, very similar to each other, but only the set that is different is here 144, here is 034. So this is specific for leap year and this is specific for general year, and we can easily calculate, by looking at each other. 144 is what we can relate this with, 12 squared, right? 025 gives us, is related with 5 squared, so 036 is related with 6 squared, and 146 is close to 144, so this must be 12 squared plus 2. So that is our technique for remembering this. And we have code for month now. Now we need to work upon year. We have only defined the code for the code for type of year. Now we need to find the exact code for the year. Now let's do that again, okay? Now for year, let's revise that first, okay? We had found that for general year the number of odd days is 1, and for leap year the number of odd days was 2. Let's check that fact, okay? In general year there are 365 days, and if divided by 7, this results to 52 weeks and 1 odd day, right? And in leap year there are 366 days, which again divided by 7 leaves us with 52 weeks and 2 days. We were very right with our calculations, right? 1 day odd day for general year, 2 days of odd days for leap year. Now since we have numbers in more than hundreds and 200s, let's figure out for them also, okay? So let's suppose now what we must do is, if in the number of year, let's find out if in the century years how many numbers of odd days are there in century years, right? So let's say in 100 years we can find the number of leap years if we divide 100 by 4, and this will give us 25 leap years, right? But 25 is not the correct answer, because 100 itself is not a leap year. So the centuries that are not exactly divisible by 400 are not leap years, so 100 is not a leap year. So to find out the right number of leap year, we have to subtract 1. This gives us 24. So we have 24 leap year, and 100 minus 24 general year. This gives us 76 years are general years and 24 years are leap years. So in 24 leap years, we know that in each leap year there are 2 number of odd days, right? So 24 times 2, plus in each general years there is 76 times 1 odd days. That gives us 24 times 2 is 48, plus 76 times 1 is 76. 8, 6, 14, 4, carry 1, 7, 4, 11, 1, 12, 124. Now if we perform modular 7 here also, then we will have 7 times 1 is 7, right? 5, 4, 54. 7 times 7 is 49. 54 minus 49 gives us 5 number of odd days in a century. Now let's take this value, the number of odd days, in a century, that is equal to 5. So in 200, in the another 100 years, we will have another 5 number of odd days. In another number of 100 years, we will have another 5 number of odd days. And in 400, in another 100 years, we will have 5 plus 1 is equal to 6 number of odd days. Why? Because the century that's exactly divisible by 400 is also a leap year. So we must add 1 leap year into that number, right? Or we can say that for if 400 is a leap year, then 400 must have 2 number of odd days, right? In counting from 1 to 300 to 400, in 100 years we took 400 as the general year. That means for 400 we added 1 only. Now the remaining number of odd days is 2 minus 1, 1. So we must be adding 1 in that to make the calculations right. So similarly, if we go down, we have 500. Then in 500 we will have another 5 number of odd days. In between from 500 to 600 we will have another 5. In 700 we will have another 5. 800 we will have another 5. 900 we will have another 5, right? And 1000 or 1000 we will have another 5. 1100 we will have another 5. 1200 we will have another 5. And 1300 we will have another 5. Now if we again find the cumulative frequency odd days, then we can see here 5 is 5. Alright, so for that, in 100 years we have 5 number of odd days. Now in 200 years, 5 plus 5 gives us 10. Similarly 5 15, 5 15 times 15 plus 6 is 21, and we have ignored the fact here for now, but let's add. In 800 we have to add 1 for the leap year, that is in 800th year, that has 2 number of odd days, but we, while calculating 5, we only added 1. So in another 1200 we have to add another 1. So this will give us 21 times 21 plus 5 is 26, plus 5 is 31, plus 5 is 36, plus 6 is 42, plus 5 47, plus 5 52, plus 5 57, plus 6 63, plus 5 68. Now let's calculate the mode 7, right? Mode 7 in is, then we have 5 here, 3 1 0. 7 times 3 is 21, so 5. 7 times 4 is 28, so 3. 7 times 4 is 28, and 7 times 5 is 35, and 1. 7 times 6 is 42, so 0. 7 times 6 is 42, plus 5 47. 7 times 7 is 49, so 3. 7 times 8 is 56, plus 1. 7 times 9 is 63, so 0. 7 times 63 is 7 times 9 is 63, so plus 5. We can see here, when we go from 100 to 1200, the number of odd days repeats like 5 3 1 0, 5 3 1 0, 5 3 1 0, 5 3 1 0, right? And for finding the number of odd days up to the 100, for some 100 something like 128, 158, for that we have to calculate the number of odd days up to 100, right? So for 100 we have 5, for 200 we have 3, for 300 we have 1, for 400 we have 0, right? While writing in this fashion, we may go a step ahead and we may say that we can break this year apart into some 400 times em number plus some century year, right? For the we are calculating for the century part of this year, right? Some 1500, 1600, 1700, and that part of the year. So 400 m, if m is equal to 0, then 400 times 0 is 0, right? So the next one is the century years are 100, 200, 300, right? And then when m is equal to 1 for the first time, 400 times m gives us 400, right? Again, if we say here m is equal to 1. If we continue like that, then 400 plus 100 is equal to 500. 400 plus 200 is equal to 600. 400 plus 300 is equal to 700. Now again m is equal to 2, right? 400 times 2 is 800. So here nothing, 800, right? Here we say 800 plus 100. Here 800 plus 200. 800 plus 300. Now again 1200 is when m is equal to 3. 400 times 3 is 1200. Now if we look at the pattern here, we can divide each century years, how any number of century years, into 400 m plus something, where something this century years, this remaining century years are only 100, 200, 300, 100, 200, 300, 100, 200, 300, right? For 100, 200, 300, let's see their specific codes here. For 100 the code is 5, for 200 the code is 3, for 300 the code is 1, for 105, 203, 301, 105, 203, 301. And again here if we add 1200 plus 100, this gives us 1300, and for that the code is 5, right? So we have a specific code for the little century years, right? Little, or we can say little century years, code for the little century years. And these codes are: for 100 the code is 5, for 200 the code is 3, for 300 the code is 1. And this is nothing difficult, right? Because if we think about the odd numbers 1, 3, 5, these are them, and the relation is just opposite. The smallest gets the biggest, the middle one gets the middle, and the biggest gets the smallest. The relation is opposite. We have to just memorize that. And for 400 or any 400 m, we can see here, for 400 m here is 0, for 400 here is 0, 800 0, 1200 0. So we can say that for any 400 m we have the number of odd days is 0. So if we break the year apart into 400 m plus something, then for 400 m we can completely ignore that. Now this is for century years, and now let's go for the leap years. No, for the remaining years. So for finally calculating, for the number of odd days in a year, we did one homework before that. That is finding the number of, finding the number of the odd days in the little century years, and also finding the number of odd days in the leap century year. This will help us in many ways. This will make our calculations a lot easier, this century leap year, and that is the multiple of 400 m, because the code for that is 0, and we can completely ignore the 400 times something part of the year. And suppose we are calculating the day of a year, then for that, since the year hasn't completed, right, the year is still going on, we have to subtract 1 from it, right, so that we can calculate the number of odd days up to year minus 1. And then after that, in this year there is we have month, right, and in month we have assigned the respective code by shifting the actual number of odd days just one step down. That gives us the number of odd days. Suppose we have, for if we want to calculate the number of odd days for the month May, right, we have to look for the number of odd days up to the month just before May, right, that will be April. So we shifted those code one step down. And then similarly here also, since this year is running right now, we must subtract 1 from this year, so we have a number that is year minus 1, and we need to find the number of odd days up to this year minus 1. And the running year will have the codes in the months and days. So first we need to subtract 1 from the year. This is crucial part of the trick. Then we need to break or expand expand this year minus 1 into some century leap years, closest but a little bit lower century leap year, plus some century years and some remaining years, plus remaining years. Here century leap year must be in the form 400 times m, right? 400 times m. That could be 400, 800, 1200, 1600, 2000, 2400 and so on, right? And this, for this 400m the code is 0, so we completely ignore this, right? The code is 0, 0 makes no contribution here. For century years, if the century year is 100, we have the code 5. If it's 200, then we have the code 3. If it's 300, then we have the code 1. We are already fixed about the century years. Now the problem lies with the remaining years, right? For the calculation of or number of odd days in the remaining years, first we have to find out how many leap years are there, and for that we can do, if this value is r, then we can integer divide r by 4, and we will find, we'll have an integer I, where this I will give us the number of leap years, right? Number of leap years. Now as soon as we find the number of leap years, we must also have to find the number of general years, right? Because in between these years there are some leap years and there are some general years. For finding the leap year, we divide by 4, and that integer that is remaining with us, that is I, will give us the number of leap years. And since there are I number of leap years in R, then R minus I number of years must be general. And we know from the previous calculation that if it's a leap year, for leap year there are 2 number of odd days, and for general year we have 1 number of odd days. So the last code for the remaining years will be given by this formula, and which is simplified to the 2 times I is 2I, plus 1 times R is R, minus 1 times I is I. This will give us 2I minus I plus R. So our last code is given by I plus R, where R is the remaining years and I is the number of leap years. So we have done everything, right? For remaining years, the code is I plus R, where I is the number of leap years in those remaining years, and R is remaining years. So let's do this in reverse, okay? Let's go from the year. First, what do? We break the year, we subtract 1 from the given year, because we want to find out the number of odd days up to the previous year, because this year is currently running, and for this year we move on to the M part, month part and day part. So for year we subtract 1 from this, and then break or expand that year minus 1 value into some century leap years, some century years and some remaining years. For century leap years, we have already calculated that for 400m, right? Some multiplication of 400, the code is 0. For century years, if it's 100, then the code is 5. If it's 200, then the code is 3. If it's 300, then the code is 1. Or we can say I'm saying code and number of odd days alternately. These two mean the same. And for the remaining years, we need to first find for finding the number of odd days in the remaining years, we need to first find the number of leap years and then the number of general years. And for finding the number of leap years, we divide R by 4. This will give us an integer I. And then for finding the general year, we simply subtract I number of leap years from R, that is R minus I. And I times 2 is 2I plus and then number of, in general years there are 1 number of odd days in each, right? In leap years there are 2 number of odd days in each leap years. So this gives us a value I plus R, which is the required number of odd days in the remaining years. So in remaining years, the number of odd days is I plus R. We have calculated for century year, we have calculated for remaining year, and for century leap year there is no number of odd days. So we are finished with the year. Now we move on to the month part, right? For month part we have specific codes for general and specific codes for leap, right? And this will give us the corresponding value for, we have to, for finding the code of a month, we have to move from up to down in the January, February, March, April in the ascending fashion. Then after month, also there is another question to be solved before going for the month, because we have to find that if the year is general or leap. If it's general, then we give it a code of -1, and if it's a leap year, then we give it a code 0. Then only we move on to the month part respectively, because if the year is general, we have to look into the general part, and if the month is year is leap, then we have to look up to the leap year column. And after that, finally we move on to the date of the day of the month, right? Last part is day of the month. And for finding the code of the day of the month, or for finding the number of odd days in these days of the month, we simply have to perform modular division by 7, and this will give us another value. So we have codes for all, right? We can say for the day we have A, and for the type of year we have B, right? And then we move on to the month part. So for that we have C, and then we move on to century. We move on to the year part by subtracting 1 from the year, and then expanding it into century leap years and century years and remaining years, right? So the next code will be here for the century years, D, and the last code for the remaining years will be E, that is I plus R. This is our theory behind the date and calendar. And if you want to revise the trick, then please go to the part 1. The whole trick is there, and this was the theory behind it. Thank you so much for watching this, and if you like my video, please give thumbs up, and if you haven't subscribed my channel yet, then please subscribe my channel, and if you have any advices, any questions, please comment down. Thank you for watching.